Right now, as you sit here reading these words or listening to this voice, there is a ball of fire hanging in the sky above you. You have known it your entire life. You have felt its warmth on your skin. You have watched it rise every morning and set every evening. You call it the sun. And for most of your life, you have probably thought of it as something enormous, something powerful, something dominant. And you would be right. The sun is, by every human standard, an incomprehensibly large object. It is so large that if you could somehow hollow it out and pour Earths inside, you would need more than 1,300,000 Earths to fill it up. Its diameter stretches across 1,391,000 kilometers. That is 109 times the diameter of our planet. The sun contains 99.86% of all the mass in the entire solar system. Every planet, every moon, every asteroid, every comet, every grain of dust floating between Mars and Jupiter, all of it combined makes up less than 0.2% of the solar system's total mass. The sun is everything. It is the gravitational anchor that holds 8 planets in their orbits. It is the nuclear furnace that makes life possible on Earth. Without it, our world would be a frozen, lifeless rock drifting through the void. So here is a question for you. What if this thing, this sun, this object so massive and so powerful that it dominates everything within billions of kilometers in every direction, what if it is actually small? What if, in the grand catalogue of stars that exist in our universe, the sun is not a giant at all? What if it is, in fact, closer to being a dwarf? And what if, somewhere out there, roughly 19,000 light years from where you are sitting right now, there exists a star so enormous, so absurdly vast, that our sun next to it would look like a grain of sand next to a beach ball? What if this star is so wide that light itself, the fastest thing in the known universe, traveling at 300,000 kilometers per second, would take nearly 9 hours just to travel around its circumference, one single time? For comparison, light goes around our sun in 14.5 seconds. What if this star is so large that if you placed it where our sun sits right now, its surface would not stop at Mercury, it would not stop at Venus, it would not stop at Earth, it would not stop at Mars, it would not stop at the asteroid belt, it would not stop at Jupiter, it would swallow all of them and keep going, reaching all the way out to the orbit of Saturn before its glowing, churning photosphere finally came to an end? That star is real. It is not a theory. It is not a computer simulation. It is not a guess. Astronomers have observed it. They have measured it. They have catalogued it. And they have given it a name that does not sound dramatic at all. A name that sounds more like a serial number than a title befitting one of the most extraordinary objects in the known universe. They call it Stephenson 218. And by certain estimates, it is roughly 2,150 times the radius of our sun. Its volume, if that estimate holds, would be approximately 10 billion times the volume of the sun. 10 billion suns. That number is so large that your brain cannot actually visualize it. Nobody's brain can. It is beyond the capacity of human imagination. And yet, the star exists. It burns. It pulsates. It sheds its own outer layers into space, like a dying emperor shedding a cloak. And one day, not millions of years from now, but perhaps thousands, perhaps even less, it will die in one of the most violent events the universe is capable of producing. But before we get there, before we travel 19,000 light years across the Milky Way to visit this impossible object, we need to understand what we are comparing it to. We need to understand our sun, not just as a bright thing in the sky, but as a machine. Because that is what a star is. It is a machine. A nuclear machine. And understanding how that machine works is the key to understanding how something as mind-bending as Stephenson 218 can exist in the first place. Let us start with the basics. Our sun is classified by astronomers as a G2V star. The G tells you its spectral type, which relates to its surface temperature. The 2 tells you where it falls within that spectral class. And the V is a Roman numeral 5, which means it is a main sequence star, what astronomers casually call a dwarf. Yes, our sun is technically a yellow dwarf. That does not mean it is small by human standards. It means it is small by stellar standards. The sun's surface temperature is approximately 5,778 Kelvin. which is about 5,500 degrees Celsius, hot enough to vaporize any known material. But compared to the hottest stars in the universe, which can have surface temperatures exceeding 40,000 Kelvin, our Sun is lukewarm. Its core, however, is a different story. At the very center of the Sun, the temperature reaches approximately 15 million degrees Celsius. The pressure is so intense that it crushes hydrogen atoms together, forcing their nuclei to merge. This process is called nuclear fusion, and it is the engine that powers every star in the universe. Here is how it works inside our Sun, deep in the core, under pressures that are roughly 250 billion times the atmospheric pressure on Earth's surface. Hydrogen nuclei, which are just single protons, are moving so fast and are packed so tightly that they overcome their natural electromagnetic repulsion. Protons are positively charged, and positive charges repel each other. Under normal conditions, you cannot push two protons together, but at 15 million degrees and under that kind of pressure, you can. When they merge, they undergo a series of reactions called the proton-proton chain. In this chain, 4 hydrogen nuclei ultimately combine to produce one helium nucleus. But here is the critical detail. One helium nucleus has slightly less mass than 4 separate hydrogen nuclei combined. A tiny fraction of mass disappears in the process. Where does it go? It becomes energy, pure energy. This is Albert Einstein's famous equation in action. E equals mc squared. Energy equals mass times the speed of light squared. Because the speed of light is such an enormous number, even a tiny amount of mass converts into a staggering amount of energy. Every single second, the Sun converts approximately 600 million tons of hydrogen into helium. And in that process, about 4 million tons of matter is converted into energy. 4 million tons of matter, vanishing every second, transformed into light and heat and radiation that streams outward in every direction. Now, this energy does not just appear at the surface of the Sun the moment it is created. The journey from the core to the surface is incredibly long and slow. The energy is generated in the core as gamma rays, the most energetic form of light. But those gamma rays immediately collide with the incredibly dense plasma surrounding them. They are absorbed, re-emitted, absorbed again, re-emitted in a random direction, over and over and over. This random walk through the radiative zone of the Sun takes, on average, somewhere between 100,000 and 200,000 years. That is how long it takes energy to travel from the core to the outer convective zone. After that, the energy is carried the rest of the way to the surface by convection, the same process that moves hot water in a boiling pot. Giant cells of plasma rise to the surface, release their energy as light, and then sink back down. When the light finally escapes the surface of the Sun, the photosphere, it then takes about 8 minutes and 20 seconds to cross the 150 million kilometers to Earth. So the light warming your face on a sunny afternoon was actually generated inside the Sun hundreds of thousands of years ago. It has been on a journey longer than the entire history of human civilization just to reach you. And this process, this nuclear fusion, is what keeps the Sun alive. It is what keeps it from collapsing under its own gravity. You see, the Sun is in a constant battle. Gravity is trying to crush it, to pull all of its mass inward toward the center. And the outward radiation pressure from nuclear fusion is pushing back, holding the star up from the inside. This balance is called hydrostatic equilibrium, and it is one of the most important concepts in all of stellar physics. As long as a star has fuel to burn, as long as fusion keeps producing energy, the star remains stable. But when the fuel runs out, a balance breaks. And that is when things get very, very interesting. Our Sun has been burning hydrogen in its core for approximately 4.6 billion years. It has enough hydrogen to continue burning for another 5 billion years or so. When it finally exhausts its core hydrogen supply, it will undergo dramatic changes. It will swell up into a red giant, engulfing Mercury and Venus, and possibly even Earth. But it will never become a supergiant. It will never become anything close to Stephenson 218, because the Sun is not massive enough. And that, right there, is the key to everything we are about to discuss. The size of a star, the kind of star it becomes, how it lives, and how it dies. All of these things are determined primarily by one factor: mass. The mass a star is born with dictates its entire life story from beginning to end, with almost no exceptions. And this brings us to a fundamental question. If our Sun is a yellow dwarf, what other kinds of stars are out there? The answer is that the universe is filled with an almost bewildering variety of stars, ranging from tiny embers barely large enough to sustain fusion, all the way up to bloated, seething monsters that defy what you might think is physically possible. Astronomers classify stars using a system that has been refined over more than a century. The most important tool in this classification is something called the Hertzsprung-Russell diagram, often abbreviated as the HR diagram. It was developed independently by Ejnar Hertzsprung and Henry Norris Russell in the early 1900s, and it remains one of the most powerful tools in all of astronomy. The HR diagram is essentially a scatter plot. On the horizontal axis, you have the surface temperature of stars, with the hottest stars on the left and the coolest on the right. On the vertical axis, you have luminosity, which is the total amount of energy a star emits per second, with the most luminous stars at the top and the dimmest at the bottom. When you plot thousands of stars on this diagram, something remarkable happens. They do not scatter randomly across the plot. Instead, they clump into distinct regions. The most prominent feature is a diagonal band running from the upper left, where you find hot, luminous blue stars, down to the lower right, where you find cool, dim, red stars. This band is called the main sequence, and it is where stars spend the vast majority of their lives, fusing hydrogen into helium in their cores. Our Sun sits right in the middle of the main sequence. Above the main sequence, in the upper right portion of the diagram, you find the giants and supergiants. These are stars that have left the main sequence, stars that have exhausted their core hydrogen and have expanded enormously. Their surfaces are cooler, which is why they appear red or orange. But because they are so incredibly large, their total luminosity is enormous. And below the main sequence, in the lower left, you find white dwarfs, the tiny, hot, dense remnants of stars that have died. Stars are also classified by their spectral type, which is directly related to their surface temperature. The classification goes O, B, A, F, G, K, M, from hottest to coolest. O-type stars are the blue giants and supergiants, with surface temperatures exceeding 30,000 Kelvin. They are extremely rare, extremely massive, and extremely short-lived. M-type stars, on the other hand, are the red dwarfs and red supergiants, with surface temperatures below 3,800 Kelvin. Red dwarfs are the most common type of star in the universe, making up roughly 70% of all stars. They are small, dim, and extraordinarily long-lived, with lifespans potentially exceeding trillions of years. Our Sun, as a G-type star, falls right in the middle of this range. But spectral type alone does not tell you everything about a star. Two stars can have the same surface temperature but be vastly different in size and luminosity. This is where luminosity class comes in. Astronomers assign luminosity classes using Roman numerals. Class Phi is for main sequence stars, dwarfs. Class 4 is for subgiants, stars just beginning to leave the main sequence. Class 3 is for giants. Class 2 is for bright giants. And Class 1 is for supergiants. The supergiant class is further divided into Ia for the most luminous supergiants and Ib for the less luminous ones, with Iab being an intermediate designation. And at the very extreme, there are stars designated Ia 0 or Ia+, the hypergiants. These are the most luminous, most massive, most extreme stars known to exist, and the red supergiants and hypergiants among them are the largest stars in the universe by volume. Now here is something that might seem counterintuitive at first, but is absolutely critical to understanding why stars like Stephenson 2.18 exist. The most massive stars have the shortest lives. You might think that a star with more fuel, more hydrogen, would last longer, but the opposite is true. More massive stars have much stronger gravity, which compresses their cores to higher temperatures and pressures. This drives fusion at a dramatically faster rate. The relationship between mass and luminosity is roughly that luminosity increases as mass raised to the power of 3.5. So, a star 10 times the mass of the Sun does not shine 10 times brighter. It shines roughly 3,000 times brighter. And because it is burning through its fuel 3,000 times faster, it lives roughly 3,000 times less long. Our Sun will live about 10 billion years. A star 10 times the Sun's mass will live only about 20 million years. A star 25 times the Sun's mass will live about 6 or 7 million years. And the most massive stars, those 40 or more times the Sun's mass, live only a few million years. In cosmic terms, that is the blink of an eye. The universe is 13.8 billion years old. These massive stars live for less than 1,000th of the universe's age. And it is precisely these massive, short-lived stars that become the red supergiants and hypergiants. So let us trace the life of one of these stars from the very beginning, because understanding how a massive star is born and how it evolves is essential to understanding how something like Stephenson 2.18 comes into existence. Every star begins its life in the same way, in a cloud. Not a cloud of water vapor like the clouds in our sky, but a cloud of gas and dust floating in the vast spaces between stars. These clouds are called molecular clouds, or sometimes giant molecular clouds, because the gas within them is cold and dense enough for molecules to form, primarily molecular hydrogen, H2. These clouds are enormous, stretching across regions of space, tens or even hundreds of light years in diameter. They contain enough material to form thousands or even millions of stars. They are cold, typically only about 10 to 20 Kelvin, which is around minus 250 degrees Celsius. And they are beautiful. When illuminated by nearby stars, they glow as nebulae, those spectacular structures you have seen in photographs from the Hubble Space Telescope and the James Webb Space Telescope. The Orion Nebula, the Eagle Nebula with its famous pillars of creation, the Carina Nebula, these are all molecular clouds in the process of forming new stars. The composition of these clouds reflects the composition of the universe as a whole, roughly 75% hydrogen and 25% helium, with trace amounts of heavier elements like carbon, nitrogen, oxygen, silicon, and iron. These heavier elements were created by previous generations of stars that lived and died before this cloud even formed. This is important. The heavy elements in any given molecular cloud were forged in the cores and explosions of stars that came before. The universe is a recycling machine. Stars create elements, they die and scatter those elements into space, and new stars form from the enriched material. Every generation of stars contains a slightly higher proportion of heavy elements than the last. Now, a molecular cloud can remain stable for millions of years, just floating in space, cold and dark. But something has to disturb it. Something has to compress a region of the cloud enough to trigger gravitational collapse. This trigger can take many forms. It could be the shock wave from a nearby supernova, the death explosion of a previous massive star rippling through the interstellar medium and compressing the cloud. It could be the density waves associated with the spiral arms of a galaxy, squeezing the gas as the cloud passes through. It could be a collision between two molecular clouds, or it could be the radiation and stellar winds from nearby hot, young stars. Whatever the trigger, once a region of the cloud is compressed enough, gravity takes over. There is a critical threshold called the Jeans mass, named after the British physicist James Jeans. If a clump of gas exceeds the Jeans mass for its given temperature and density, the gravitational force pulling the clump inward exceeds the thermal pressure pushing outward, and the clump begins to collapse. As it collapses, it fragments into smaller clumps, each of which may go on to form an individual star or a small group of stars. The collapsing fragment contracts under its own gravity, heating up as gravitational potential energy is converted into thermal energy. As the gas gets hotter and denser, it begins to glow, first in infrared light. At this stage, the object is called a protostar. It is not yet a true star because nuclear fusion has not yet ignited in its core. But it is getting there. Because the original cloud was rotating, even very slowly, the collapsing fragment also rotates. And as it contracts, it spins faster, the same way an ice skater spins faster when pulling their arms in. This conservation of angular momentum causes the material to flatten into a rotating disk around the protostar, called a protostellar disk or protoplanetary disk. Some of this disk material will eventually form planets, moons, asteroids, and comets, but most of it continues to fall onto the protostar, adding to its mass. The protostar continues to contract and heat up. When the temperature at its core reaches approximately 10 million Kelvin, something extraordinary happens. The protons at the center are moving so fast and are so tightly packed that they begin to fuse. Hydrogen fusion ignites, and at that moment, a new star is born. For a star with a mass between about 10 and 40 times the mass of the Sun, the conditions at birth are extreme. The core temperature is high enough that the dominant fusion process is not the proton-proton chain that powers our Sun. Instead, it is the CNO cycle, the carbon-nitrogen-oxygen cycle. In this process, carbon, nitrogen, and oxygen atoms act as catalysts, facilitating the fusion of hydrogen into helium through a series of intermediate reactions. The CNO cycle is far more temperature-sensitive than the proton-proton chain. A small increase in temperature dramatically increases the fusion rate. This means the core of a massive star is furiously energetic, generating so much energy that the core becomes fully convective, with hot plasma churning and mixing throughout. On the main sequence, these massive stars are already tremendously luminous, shining 10,000 to 100,000 times brighter than the Sun. Their surface temperatures are high, typically 25,000 to 32,000 Kelvin, making them blue or blue-white in color. They have spectral types of early B or late O. They are the brilliant blue diamonds of the stellar world. But their lives are short. A star of 15 solar masses will spend only about 12 million years on the main sequence. A star of 25 solar masses will spend only about 6 or 7 million years. And then the core hydrogen runs out. The core, which has been converting hydrogen into helium for millions of years, is now predominantly helium. And helium, at the temperatures and pressures present in the core at this stage, cannot fuse. Not yet. Fusion in the core ceases, and when fusion ceases, the outward radiation pressure that has been holding the star up against gravity disappears. But the star does not collapse completely. What happens instead is that hydrogen continues to fuse in a shell surrounding the inert helium core. This hydrogen shell burning generates a tremendous amount of energy, actually more energy than was being produced when the core itself was fusing. This extra energy causes the outer layers of the star to expand enormously, and as the outer layers expand, they cool. The surface temperature drops from 25,000 Kelvin or more down to 4,000, then 3,500, then even lower. The star goes from being a brilliant blue main sequence star to becoming a swollen, cool red behemoth. It has left the main sequence and become a red supergiant. This transition happens relatively quickly in astronomical terms. The star passes through intermediate stages, sometimes briefly becoming a yellow supergiant or even a yellow hypergiant before cooling further into the red supergiant phase. Some stars may briefly pass through the Cepheid instability strip, becoming pulsating variable stars for a short time. But for most massive stars in the 10 to 30 or 40 solar mass range, the final destination is the red supergiant branch of the HR diagram. And once a star becomes a red supergiant, its properties become extreme. Its surface temperature has dropped to somewhere between 3,200 and 4,100 Kelvin. This is actually cooler than the filament in some incandescent light bulbs, but its radius has ballooned to hundreds, sometimes over 1,000 times the radius of the Sun, because luminosity depends on both temperature and surface area. And because the surface area has increased by factors of millions or even billions, the total luminosity remains extremely high, typically tens of thousands to hundreds of thousands of times the luminosity of the Sun, despite the much cooler surface. These are the red supergiants. They are the largest stars by volume in the entire universe. Inside a red supergiant, things have become complex. The core is still predominantly helium, surrounded by a hydrogen-burning shell. But eventually, the helium core contracts enough and heats enough that helium fusion ignites. Helium nuclei, which are alpha particles, fuse to form carbon through the triple alpha process, a reaction that requires 3 helium nuclei to combine almost simultaneously. This is actually a very unlikely reaction, but at the extreme temperatures and densities in the core of a supergiant it proceeds. Helium fusion in the core begins smoothly, either while the star is still expanding, or once it has already reached the red supergiant stage. At the surface, you would notice very little change. The star continues to shine as a red supergiant. But now, the star has developed deep convection zones that extend from the surface more than halfway down to the core. These convective zones bring material from deep within the star up to the surface, a process called dredge up. The surface chemistry changes. Nitrogen becomes enriched, because the CNO cycle deep within the star converts carbon and oxygen into nitrogen. So, if you were to analyze the spectrum of a red supergiant, you would find unusually high nitrogen abundances, a telltale sign of the CNO cycle's work being brought to the surface. Red supergiants are also losing mass at a prodigious rate. The surface gravity of a red supergiant is extremely low because the star's enormous radius means the surface is far from the center of mass. This weak surface gravity, combined with the intense radiation pressure from within, drives powerful stellar winds that carry material away from the star. The mass loss rate for a red supergiant can be millions of times the mass loss rate of our Sun. Our Sun loses mass through the solar wind at a rate of roughly 2 to 3 times 10 to the minus 14 solar masses per year. A red supergiant can lose mass at a rate of 10 to the minus 5 or 10 to the minus 4 solar masses per year. That is billions of times faster. This shed material forms beautiful complex circumstellar nebulae around the star, visible in infrared and sometimes in visible light. You can see arcs, knots, filaments, and shells of ejected material extending for vast distances around the star. Red supergiants also pulsate. Most show some degree of variability in their brightness, with periods ranging from hundreds to thousands of days. Some are classified as semi-regular variable stars, meaning their brightness changes follow a rough pattern, but with significant irregularity. The pulsation is driven by changes in opacity in the outer layers of the star. As the star expands, the outer layers cool and become more opaque, trapping energy. The trapped energy builds up, causing the star to expand further. But then the opacity drops, energy escapes and the star contracts. This cycle repeats, but not perfectly, because the conditions in the star's outer layers are chaotic. Red supergiants also have enormous convection cells on their surface. While our Sun has millions of tiny granules, each about 1,000 kilometers across, a red supergiant might have only a handful of convection cells, each 100s of millions of kilometers across. These giant cells cause visible brightness variations as the star rotates, adding to the irregular variability. This is the stage of life we are dealing with when we talk about the largest stars in the universe. These are stars that were born massive, burned bright and fast on the main sequence, exhausted their core hydrogen, and then expanded into enormous, cool, luminous, pulsating, mass-shedding red supergiants. And the bigger and more luminous they are, the more extreme all of these properties become. Now, before we can truly appreciate how remarkable Stephenson 2.18 and its fellow giants are, we need to address a critical question. How on Earth, or more accurately, how from Earth, do astronomers figure out how big these things are? These stars are thousands or tens of thousands of light years away. They appear as nothing more than points of light, even in the most powerful telescopes. So how do you measure the diameter of something that far away? The answer involves several different methods, each with its own strengths and limitations. And understanding these methods is crucial, because as we will see, the uncertainties in these measurements are directly responsible for the ongoing debates about which star truly holds the title of largest. The most common method for determining the radius of a distant star relies on a fundamental relationship from physics known as the Stephenson-Boltzmann law. This law states that the total luminosity of a star, the total amount of energy it emits per second, is equal to 4 pi times the radius squared times the Stephenson-Boltzmann constant times the effective temperature raised to the 4th power. In simpler terms, if you know how bright a star truly is, its luminosity, and you know its surface temperature, you can calculate its radius. The equation is straightforward, but the challenge lies in determining those two input values accurately. To get the luminosity, you need to know how much total energy the star is emitting. But what you actually measure from Earth is the apparent brightness, how bright the star appears to be. A dim star that is close to us can appear just as bright as a luminous star that is far away. To convert apparent brightness into true luminosity, you need to know the distance to the star. And this is where a major source of uncertainty creeps in. Determining the distance to a star that is 10,000 or 20,000 light-years away is extremely difficult. For relatively nearby stars, distances can be measured directly using parallax, the apparent shift in a star's position, against the background of more distant stars as Earth orbits the Sun. The European Space Agency's Gaia spacecraft has been measuring parallaxes for billions of stars with unprecedented precision. But for very distant stars, especially those embedded in dense, dusty regions of the galaxy like the red supergiants in the Scuti constellation, even Gaia's measurements can be unreliable. The parallax angles are incredibly tiny, often smaller than the measurement uncertainties. Interstellar dust further complicates things by absorbing and scattering light, making stars appear dimmer and redder than they actually are, and introducing additional uncertainty into distance estimates. For red supergiants in clusters, the distance is often estimated from the cluster's radial velocity, the speed at which the cluster is moving toward or away from us, combined with a model of the Milky Way's rotation. This kinematic distance method can provide reasonable estimates, but the uncertainties are often 20, 30, even 50% or more. The effective temperature is determined from the star's spectrum. By analyzing the absorption lines in a star's light, the characteristic patterns of wavelengths absorbed by different elements and molecules in the star's atmosphere, astronomers can classify the star's spectral type and estimate its surface temperature. But red supergiants have extended, complex, layered atmospheres with lots of molecules, particularly titanium oxide, which creates strong absorption features. The temperature you derive can depend on exactly which spectral features you analyze and what models you use. Different studies can arrive at different temperatures for the same star. So the Stefan-Boltzmann method gives you a radius, but that radius inherits all the uncertainties in the distance and the temperature. If the distance is wrong by 30%, the luminosity is wrong by a factor related to the square of the distance, and the radius will be significantly off. If the temperature is wrong by a few hundred Kelvin, the radius can change by a large margin because it depends on temperature to the negative second power. A more direct method involves actually measuring the angular diameter of a star. This is the apparent size of the star on the sky, typically measured in milliarc seconds, which are incredibly small angles. 1 milliarsecond is 1/3,600th of a degree. To measure such tiny angles, astronomers use a technique called stellar interferometry. By combining the light from multiple telescopes separated by large distances, they can achieve the angular resolution needed to resolve the disks of the largest, nearest supergiants. In 2012, the AMBER instrument on the Very Large Telescope in Chile was used to measure the angular diameter of Scuti, yielding a value of 5.48 plus or minus 0.1, 0 milliarseconds. Combined with an assumed distance, this gave a physical radius. But once again, the derived physical radius depends on the assumed distance. Other direct methods include lunar occultations, where the moon passes in front of a star and the rate at which the star's light dims reveals its angular size, and observations of eclipsing binary systems, where one star periodically passes in front of another, and the light curve can be used to determine the star's sizes relative to their orbital separation. However, lunar occultations are only possible for a few supergiants that happen to lie near the moon's path across the sky, and eclipsing binaries are relatively rare among supergiants. A newer technique involves studying the maser emissions from the circumstellar material around red supergiants. Masers are the microwave equivalent of lasers, naturally occurring amplified emissions at specific wavelengths, typically from molecules like water, H2O and silicon oxide, SiO, in the gas surrounding the star. Using very long baseline interferometry, or VLBI, which links radio telescopes across vast distances to create an effective telescope thousands of kilometers in diameter. Astronomers can measure the positions of these masers with extreme precision. This allows them to determine parallax distances to the masers, and by extension to the star, with much greater accuracy than optical methods in some cases. The key takeaway from all of this is that measuring the sizes of distant giant stars is extraordinarily difficult. The numbers you see quoted for the radii of the largest stars are not exact. They are estimates, often with significant uncertainties. And different studies, using different methods, different data, and different assumptions, frequently arrive at different values for the same star. This is not a failure of science. It is the reality of trying to measure objects that are incomprehensibly far away surrounded by dust, embedded in crowded star fields, and constantly changing in size as they pulsate. It is actually a testament to the ingenuity of astronomers that they can determine these sizes at all. With this foundation, we're now ready to begin our journey through the largest stars known to exist. We will start with stars that are, by stellar standards, respectably large, and then work our way up, step by step, through increasingly massive and luminous objects, each one making the previous one look modest by comparison. And at the end of this journey, we will arrive at Stephenson 2.18 and the fascinating debate that surrounds it. Let us begin with a star you can see with your own eyes on any clear night. A star that has been known to humanity for thousands of years. One of the most famous stars in the entire sky. Betelgeuse. The name itself comes from an Arabic phrase, likely meaning the hand of Orion, or the armpit of the central one, depending on which linguistic interpretation you follow. It marks the left shoulder of the constellation Orion, and it is unmistakable because of its distinctive reddish-orange color. When you look at Orion on a winter night, and you see that slightly orange star in the upper left corner of the constellation, that is Betelgeuse, and what you are looking at is a red supergiant. Betelgeuse is located approximately 700 light-years from Earth, which, in cosmic terms, is practically in our backyard. It is one of the brightest stars in the night sky, typically fluctuating around an apparent magnitude of 0.5, although it varies considerably because it is a semi-regular variable star. Its spectral type is M1 to M2 with a luminosity class of Ia to Iab, making it a luminous red supergiant. Its surface temperature is approximately 3,600 Kelvin, and its radius is estimated at approximately 764 solar radii. That means Betelgeuse is about 764 times wider than our Sun. If you placed Betelgeuse at the center of our solar system, its surface would extend well beyond the orbit of Mars. The asteroid belt between Mars and Jupiter would be inside this star. Betelgeuse is estimated to have a mass of roughly 16 to 19 times the mass of the Sun, and a luminosity of approximately 126,000 times the Sun's luminosity. Despite its enormous size, it is actually relatively young, only about 8 to 8.5 million years old. It was born as a hot blue O-type or early B-type star on the main sequence, lived its brief main sequence life, exhausted its core hydrogen, and expanded into the red supergiant we see today. It is a member of the Orion OB1 stellar association, a loose grouping of young massive stars in the Orion region. Betelgeuse made international headlines in late 2019 and early 2020 when it underwent a dramatic dimming event that became known as the Great Dimming. The star's apparent brightness dropped to about 1/3 of its normal value, the faintest it had been in over a century of observations. For a brief, exciting, and slightly terrifying period, people wondered if Betelgeuse was about to explode as a supernova. It was not. Subsequent research revealed that the dimming was caused by a massive surface eruption, a coronal mass ejection far more powerful than anything our Sun produces, that expelled a huge cloud of hot gas from the star's surface. As this gas moved away from the star and cooled, it condensed into a cloud of dust that partially blocked our view of the star, causing the apparent dimming. This event was a powerful reminder of how dynamic and violent these red supergiants are, constantly shedding material and reshaping their immediate environments. When Betelgeuse does eventually explode as a supernova, which astronomers estimate will happen sometime within the next 100,000 years, it will be a spectacular sight. At 700 light-years away, it would appear roughly as bright as the half-moon, easily visible during the day. It would be the brightest supernova visible from Earth in recorded history. But importantly, at that distance, it would pose no threat to our planet. No dangerous radiation, no destructive shockwaves, just a magnificent light show that would last for several months before fading away. Betelgeuse is impressive. 764 times the radius of the Sun is no small feat. But it is far from the largest star known. It does not even crack the top 10, so let us keep climbing. Antares is another famous red supergiant, the brightest star in the constellation Scorpius, and one of the brightest stars in the night sky. Its name means rival of Mars in Greek, because its reddish color often leads people to confuse it with the planet Mars when the two appear close together. Antares is located approximately 550 light-years from Earth. It is actually a binary star system. The primary component, Antares A, is the red supergiant, with a spectral type of M1, 5 and a luminosity class of Iab to Ib. Its radius is estimated at approximately 680 solar radii. Its luminosity is roughly 75,000 to 90,000 times the Sun's. It is a member of the Scorpius-Centaurus Association, a nearby grouping of young, massive stars. Antares A and Betelgeuse are the only two first-magnitude red supergiants visible from Earth, making them the two most prominent examples of their kind in our sky. Moving up the ladder, we encounter Mu Cephei, a star in the constellation Cepheus that has been known for centuries by a much more poetic name. William Herschel, the astronomer who discovered Uranus, observed this star in the late 18th century and was so struck by its deep saturated red colour that he called it the Garnet Star, and the name stuck. Mu Cephei is located approximately 2,840 light-years from Earth. It is a red supergiant with an estimated radius of approximately 972 solar radii, plus or minus 228. That uncertainty range is large, reflecting the difficulty of measuring distant supergiants. Its luminosity is approximately 340,000 times the Sun's, making it one of the most luminous stars visible to the naked eye, though just barely, at an apparent magnitude of around 4. Mu Cephei is a semi-regular variable star, pulsating with periods of roughly 860 days. Now, let us talk about a star that dominated the largest star discussion for years, and whose story perfectly illustrates the challenges of stellar measurement, Ui Scuti. This star is located in the constellation Scutum, approximately 5,900 light-years from Earth. It was first catalogued in 1860 by German astronomers working on the Bonner Durchmusterung stellar catalogue, a comprehensive survey of the sky. It was designated BD-12 degrees 5055. When it was observed again, astronomers noticed it had changed slightly in brightness, indicating it was a variable star. Following the naming convention for variable stars, it was given the designation Ui Scuti, denoting it as the 38th variable star discovered in the constellation Scutum. In 2012, a team of astronomers used the amber interferometry instrument on the Very Large Telescope in Chile to directly measure the angular diameters of 3 red supergiants near the galactic center region. One of these stars was Ui Scuti. They measured an angular diameter of 5.48 plus or minus 0.10 milliarc seconds. Now, to convert this angular diameter into a physical radius, they needed the distance to the star. The distance they used was 2.9 plus or minus 0.317 kiloparsecs, which is about 9,500 light-years. This distance had been derived in a 1970 study based on spectral modelling. Using this distance, they calculated a radius of 1,708 plus or minus 192 solar radii. This made Ui Scuti the largest known star at the time, and the result was widely reported in popular science media. But the story does not end there. More recent measurements from the Gaia spacecraft provided a new parallax-based distance to Ui Scuti. The Gaia Early Data Release 3, combined with analysis by Baylor Jones and colleagues in 2021, placed Ui Scuti at a much closer distance of approximately 1,800 parsecs, or about 5,900 light-years. This is significantly less than the 9,500 light-years used in the 2012 study. And because radius depends on distance, a closer distance means a smaller luminosity and a smaller radius. A 2023 study published in the monthly notices of the Royal Astronomical Society recalculated Ui Scuti's parameters using updated data and found a radius of 909 solar radii, a luminosity of 124,000 solar luminosities, and an effective temperature of 3,550 Kelvin. Some estimates using the Gaia Data Release 2 parallax place the radius even lower, at around 755 solar radii. So Ui Scuti went from being touted as the largest known star at 1,708 solar radii to having a revised radius of approximately 755 to 909 solar radii. It is still an enormous star, far bigger than Betelgeuse, but it was dethroned from its record-holding position. This is a perfect example of why distance matters so much in these measurements, and why claims about the largest star should always be accompanied by an understanding of the uncertainties involved. The angular diameter measurement from the VLT was solid. It was the assumed distance that made all the difference. Now let us continue upward to a truly extraordinary object, VY Canis Majoris. This red hypergiant, located in the constellation Canis Major, approximately 3,900 light-years from Earth, has been a central figure in discussions of extreme stellar size for decades. Its spectral type is approximately M3 to M5, and it has been classified as a luminosity class Ia, a red hypergiant. The most commonly cited and well-established radius for VY Canis Majoris comes from a 2011 study using the Very Large Telescope, which estimated a radius of approximately 1,420 plus or minus 120 solar radii. At this size, if VY Canis Majoris were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Its luminosity is approximately 270,000 times the Sun's, and its mass is roughly 17 solar masses. But VY Canis Majoris is not just notable for its size. It is one of the most dramatic and extreme objects in stellar astrophysics. The circumstellar environment around VY Canis Majoris is breathtaking. The star is shedding mass at a tremendous rate, and the ejected material has formed a complex, asymmetric nebula of arcs, knots, and filaments, extending for thousands of astronomical units around the star. Observations with the Hubble Space Telescope revealed multiple discrete mass ejection events, each creating distinct structures in the surrounding nebula. These ejection events are not continuous, but episodic, suggesting violent outbursts at irregular intervals. The star also displays powerful maser emissions from water, silicon oxide, and hydroxyl molecules in its circumstellar envelope. These masers have been used to map the distribution and velocity of material around the star with extraordinary precision, providing insights into the mass loss process. Very long baseline array observations of these masers have been used to derive an accurate parallax distance to VY Canis Majoris, helping to constrain its physical properties better than would otherwise be possible. VY Canis Majoris is approximately 8.2 million years old, which may sound old, but is actually very young in stellar terms. It was born as a hot, massive, blue main sequence star, and has evolved through the main sequence, off the main sequence, and into its current red hypergiant state in just a few million years. And it does not have much time left. Within the next few 100,000 years, VY Canis Majoris will exhaust the remaining fuel in its core and undergo a catastrophic core collapse, resulting in a supernova explosion. Given its mass and current state of extreme mass loss, it may first evolve through a blue loop back to higher temperatures, potentially becoming a Wolf-Rayet star before exploding. Or it may explode directly as a red supergiant. Either way, the end is coming, cosmically speaking. NML Cygni is another red hypergiant that deserves mention in this progression. Located in the constellation Cygnus, approximately 5,300 light-years from Earth, it has an estimated radius of roughly 1,183 solar radii and a luminosity of approximately 270,000 times the Sun's. Like VY Canis Majoris, it is surrounded by a dusty envelope and is heavily obscured in visible light, detectable primarily in infrared and radio wavelengths. Its distance was determined using very long baseline array observations of silicon oxide masers, which gave a parallax-based distance of about 1.61 kiloparsecs. Now, let us move to a star that recently underwent one of the most dramatic transformations ever observed in real time, WOHG 64. This star is not in the Milky Way at all. It is located in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way approximately 163,000 light-years from Earth. That enormous distance means we cannot study it in the same detail as Milky Way stars, but because the Large Magellanic Cloud is at a reasonably well-known distance, the uncertainty in the star's luminosity and radius is actually better constrained than for many Milky Way supergiants where individual distances are poorly known. WOHG 64 was identified as a red supergiant with a mass of roughly 25 to 28 solar masses, surrounded by a thick torus-shaped envelope of dust and gas. Its estimated radius was approximately 1,540 solar radii, making it one of the largest stars with a well-determined radius. For years it was a strong contender for the title of largest known star. But then something remarkable happened. Observations conducted in 2024 and reported in early 2025 revealed that WOHG 64 had dramatically changed. It had transitioned from a red supergiant to a yellow hypergiant. Its surface temperature had increased significantly, meaning it had contracted. Its radius shrank from approximately 1,540 solar radii to roughly 800 solar radii. It had effectively halved in size in what, astronomically speaking, was the blink of an eye. This was extraordinary. Astronomers had never before directly observed such a dramatic transformation in a distant star in real time. It was not dying, as some had initially speculated. It was evolving. It was going through a transition that stellar evolutionary models predict, but that had never been witnessed at this scale. The observation was a reminder that stars are not static objects. They change. They breathe. They expand and contract. And sometimes they do so in ways that we can actually see, even when they are 163,000 light-years away. The story of Watch G64 also reshaped the discussion about the largest stars. A star that was once near the top of the size rankings suddenly shrank to less than half its former radius. The universe, it seems, does not care about our rankings. And now, let us approach a star that has more recently entered the conversation as a leading contender for the largest star in the Milky Way. Its name is RSGC1 F01. And while it does not have the internet fame of Scuti or the headline-grabbing estimated size of Stephenson 2.18, it may in fact be the most reliably measured giant among them. RSGC1 F01 is a member of the open star cluster RSGC1, which stands for Red Supergiant Cluster 1. This cluster is located approximately 22,000 light-years from Earth in the constellation Scutum, the same constellation that hosts Scuti and the Stephenson 2 cluster. RSGC1 was discovered in 2006 by a team led by Donald F. Figure of the Rochester Institute of Technology, using data from the 2-micron all-sky survey, the Spitzer Space Telescope, and ground-based near-infrared spectroscopy from the Kitt Peak National Observatory. The cluster is massive, with an estimated total mass of about 30,000 solar masses and an age of approximately 12 plus or minus 2 million years. It contains at least 14 confirmed red supergiants, more than were known in any single cluster before the discoveries of the other RSGC clusters in the same region. RSGC1 sits at the intersection of the Milky Way's Scutum Centaurus spiral arm and the northern end of the galaxy's central bar, a region of intense star formation. RSGC1 F01 is the brightest and most luminous red supergiant in the cluster. Its spectral type is approximately M3 to M5, and its effective temperature is about 3,550 Kelvin. Its luminosity has been estimated at approximately 335,000 times the Sun's luminosity. Two separate studies have estimated its radius. A 2020 study led by Roberta M. Humphreys of the University of Minnesota, using observations from the SOFIA telescope's forecast instrument and the Large Binocular Telescope's LMIR cam, derived a radius of 1,530 solar radii. A more recent 2023 study, led by Leen Dessin of KU Leuven, Belgium, using observations from the Atacama Large Millimeter-Submillimeter Array, or ALMA, found a radius of approximately 1,450 solar radii. The uncertainty range spans from about 1,100 to 1,860 solar radii. What makes RSGC1 F01 particularly important is that its properties are measured using well-understood methods. Its cluster membership is not disputed, and its parameters fall within the range predicted by stellar evolutionary theory. Unlike Stephenson 2.18, whose estimated radius of 2,150 solar radii exceeds the theoretical Hayashi limit, and is based on uncertain distance and questionable cluster membership, RSGC1 F01's radius of 1,450 to 1,530 solar radii is large, but physically plausible. It represents, in a sense, the kind of extreme size that the universe actually allows a stable star to achieve. Our SGC-1, F01, is also experiencing extreme mass loss at a rate of approximately 1.7 times 10 to the minus fifth solar masses per year. That means it is losing about 17 millionths of a solar mass every year. This might sound tiny, but over millions of years it adds up to a significant fraction of the star's total mass. This mass loss is sculpting a circumstellar envelope around the star and will play a role in determining the star's ultimate fate. With our SGC-1, F01 in mind, we are now ready to return to the star that inspired this entire journey, Stephenson 218. Let us tell its story from the beginning. In 1990, an American astronomer named Charles Bruce Stephenson was analyzing data from a deep infrared survey of the sky. Infrared light penetrates interstellar dust far better than visible light, which means infrared surveys can reveal stars and star clusters that are completely invisible to optical telescopes. In this survey data, Stephenson identified a cluster of stars in the constellation Scuti, in a region dense with interstellar dust and gas, deep within the Milky Way's disk. This cluster would become known as Stephenson 2, and it would turn out to be one of the most remarkable star clusters in the entire galaxy. Stephenson 2, also known as RSGC2, is located at the base of the Scutum Centaurus arm of the Milky Way, roughly 5.8 kiloparsecs, or about 19,000 light-years, from Earth. Subsequent studies revealed that the cluster contains at least 26 confirmed red supergiants, the most of any known cluster in the galaxy. A total of 80 confirmed red supergiants have been identified within a small area of the sky in the direction of Stephenson 2 and its neighbouring clusters, making this region one of the most extraordinary concentrations of massive stars anywhere in the Milky Way. The cluster has an estimated age of approximately 14 to 20 million years, meaning the stars within it formed during a massive burst of star formation at the near end of the Milky Way's central bar. When astronomers first studied the individual stars in Stephenson 2, they noticed that the brightest star in the general region of the cluster stood out. It was exceptionally bright, especially in infrared wavelengths. It was extremely cool with an estimated spectral type of about M6, unusually late even for a red supergiant. Most red supergiants fall in the M0 to M5 range, so M6 is pushing the extreme end. This star was initially given the designation number 1, DFK1. In the first comprehensive analysis of the cluster by Davies, Figure, and Kudrytsky in 2007, they noted that this star was abnormally bright and had a slightly different proper motion than the other cluster members. Based on these properties, they did not consider it a certain member of Stephenson 2. Instead, they suggested it might be an unrelated red supergiant that just happens to appear near the cluster on the sky. In 2010, a separate study by Deguchi and colleagues analyzed the same star as part of a larger study of stars in the Stephenson 2 region. In their numbering system, this star was given the number 18, and so it became commonly known as Stephenson 218, or STU 18. To avoid confusion between different numbering systems, astronomers sometimes refer to it as Stephenson 2DFK1, but in popular media and on the internet, Stephenson 218 is the name that stuck. In 2012, a study by Thomas and colleagues used the Australia Telescope Compact Array and the Dusty Radiative Transfer Model to derive the physical properties of Stephenson 218 and dozens of other red supergiants across the galaxy. For Stephenson 218, they derived a bolometric luminosity of approximately 440,000 times the Sun's luminosity and an effective temperature of 3,200 Kelvin. Plugging these numbers into the Stefan-Boltzmann law yielded a radius of approximately 2,150 solar radii. 2,150 solar radii. That number immediately attracted attention, because it is much larger than the theoretical upper limit for red supergiants predicted by stellar evolutionary models. Let us unpack why this is significant. In 1961, the Japanese astrophysicist Chushiro Hayashi published a groundbreaking paper on the structure of convective stars. He established what is now known as the Hayashi limit, sometimes called the Hayashi track. This is the boundary on the Hertzsprung-Russell diagram beyond which a star cannot maintain hydrostatic equilibrium as a fully convective object. In practical terms, For a red supergiant, the Hayashi limit sets a minimum effective temperature of roughly 3,400 to 3,500 Kelvin for stars at solar metallicity. A star cooler than this limit would be so extended and so loosely bound that its outer layers could not be gravitationally held by the star. They would simply dissipate into space. This translates to a maximum radius of approximately 1,500 solar radii for a stable red supergiant. The estimated temperature of 3,200 Kelvin for Stephenson 2, 1/8, is below the Hayashi limit, and the estimated radius of 2,150 solar radii is far above the predicted maximum. This immediately raised questions. Was the measurement wrong? Was the star genuinely in a state of extreme instability, actively shedding its outer layers in a dramatic mass loss episode? Or was there a problem with the input assumptions? The most recent comprehensive study of Stephenson 2, 1/8 by Humphreys and colleagues in 2020 derived a bolometric luminosity of 630,000 solar luminosities based on spectral energy distribution integration using published photometric data from multiple wavelengths, assuming a distance of 5.8 kiloparsecs. However, this study also noted that Stephenson 2, 1/8 spectral energy distribution is peculiar and cannot be well fitted to standard interstellar reddening laws. This suggests that the star may have additional circumstellar extinction, that it is embedded in its own dusty envelope, which would mean its true luminosity is even higher than 630,000 solar luminosities. But it could also mean that the star's distance or other properties are not what they appear to be. The cluster membership of Stephenson 2, 1/8, remains one of the biggest sources of uncertainty. In 2012, Verheyen and colleagues analyzed silicon oxide maser emissions and infrared carbon monoxide absorption features for red supergiants in massive clusters, including stars in the Stephenson 2 region. They found that Stephenson 2, 1/8's radial velocity measured at approximately 89 km per second is significantly lower than the average radial velocity of confirmed Stephenson 2 members, which is approximately 109.3 plus or minus 0.7 km per second. This velocity difference of about 20 km per second led them to conclude that Stephenson 2, 1/8 is likely a field red supergiant, unrelated to the Stephenson 2 cluster. This matters enormously. If Stephenson 2, 1/8 is not a member of the cluster, then the assumed distance of 5.8 kiloparsecs may be completely wrong. The star could be closer, in which case its luminosity and radius would be smaller, or it could theoretically be farther, in which case they would be larger. But without reliable cluster membership, the distance is essentially unknown, and all derived properties are uncertain. There is, however, a counter-argument. Davies and colleagues in their original 2007 paper noted that the velocity difference between Stephenson 2, 1/8 and the cluster could be explained by an expanding optically thick envelope around the star. A typical outflow speed for a red supergiant stellar wind is about 20 km per second, which matches the observed velocity offset. If the star's radial velocity measurement is being influenced by material moving toward us in the stellar wind rather than reflecting the star's true space velocity, then the star might actually be a cluster member, after all. Taguchi and colleagues in 2010 proposed that Stephenson 2, 1/8 is part of a subgroup of stars near Stephenson 2 called Stephenson 2 SW, which is assumed to be at the same distance as the main cluster. So where does this leave us? Let us be honest about what we know and what we do not know. Stephenson 2, 1/8 is undoubtedly a real star. It is undoubtedly a red supergiant, possibly an extreme red hypergiant. It is undoubtedly very large and very luminous, regardless of which distance estimate you use. It has a spectral type of approximately M6, making it one of the coolest known supergiants. It shows significant infrared excess, indicating substantial circumstellar dust, likely from extreme mass loss. It displays water maser emissions, a sign of dense circumstellar material, and Davies and colleagues in 2007 suggested it might be on the brink of ejecting its outer layers and evolving into a luminous blue variable or Wolf-Rayet star. However, the frequently cited radius of 2,150 solar radii is based on a temperature of 3,200 Kelvin and a luminosity of 400 and 40,000 solar luminosities, both of which carry significant uncertainties. The temperature is below the Hayashi limit, suggesting either an extreme physical state or a measurement issue. The luminosity depends critically on the assumed distance of 5.5 to 5.8 kiloparsecs, which itself carries uncertainty greater than 50%. And the star's membership in the Stephenson 2 cluster is disputed. This does not mean we should dismiss Stephenson 2, 1.8. It means we should understand it in context. It is genuinely one of the most extreme stars ever observed. It is very likely among the largest stars in the Milky Way, possibly the largest, but the exact radius is uncertain. A more conservative estimate, assuming a higher temperature closer to the Hayashi limit and adjusted luminosity values, might place its radius somewhere around 1,200 to 1,500 solar radii, still enormous by any standard, but below the headline-grabbing 2,150. The honest answer to the question, what is the largest known star, is this. It depends on what you mean by known and how much uncertainty you are willing to accept. If you go by the highest estimated radius, Stephenson 2, 1.8 holds that distinction at approximately 2,150 solar radii, but this estimate is considered unreliable by many researchers. If you want the largest star with a well-characterized, physically plausible radius in the Milky Way, RSGC1 F01 at approximately 1,450 to 1,530 solar radii is a strong candidate. If you want the largest well-measured star across all galaxies, HV 888 in the Large Magellanic Cloud, with an estimated radius of 1,477 to 1,509 solar radii, is in the running. Canis Majoris, the long-time favourite, remains a solid entry at approximately 1,420 plus or minus 120 solar radii. And then there is the humbling case of WOHG 64, which was among the largest known at 1,540 solar radii until it contracted to about 800 solar radii right before our eyes. The universe does not respect our leaderboards. Regardless of where the final numbers settle, let us take a moment to truly appreciate the scale of what we are discussing. Let us try to make these numbers feel real, because the numbers themselves are so large that they can feel abstract. They can feel like just numbers, but they represent real physical objects burning in real space. Consider our Sun first. It has a radius of approximately 695,700 kilometers. If you could drive a car around the Sun's equator at 100 kilometers per hour, never stopping for fuel or rest, it would take you about 181 days, roughly 6 months. That is just to go around the Sun once. Now, consider a star with a radius of 1,500 solar radii, like RSGC1, F01, or WHG64, at its former size. This star would have a radius of roughly 1,043,000,000 kilometers, that is, over 1 billion kilometers. To drive around it at 100 kilometers per hour, non-stop, would take you roughly 750 years. You would not live long enough to complete the trip. Your great-great-great-great-great-grandchildren would still be driving. At the speed of light, traveling 300,000 kilometers per second, you could circle our Sun in about 14.5 seconds. To circle our SGC1, F01, light would take roughly 6 hours. 6 hours at the speed of light, just to go around the star once. Now, consider Stephenson 2, 1.8 at its claimed radius of 2,150 solar radii. Its radius would be approximately 1.5 billion kilometers. That is 10 astronomical units, roughly the distance from our Sun to Saturn. If this star replaced our Sun, Mercury would be deep inside it. Venus would be deep inside it. Earth would be deep inside it. The asteroid belt would be inside it. Jupiter, the largest planet in our solar system, would be inside it. And the star's surface would reach all the way out to Saturn's orbital distance. Every rocky planet, every gas giant inner to Saturn would simply cease to exist, engulfed by a star so large that our entire inner solar system would be a tiny bubble in its interior. To fly around Stephenson 2 to 18 in a commercial airplane at 900 kilometers per hour would take more than 1,100 years. and at the speed of light, the circumference would take roughly 8 to 9 hours to traverse. The volume comparisons are even more staggering. Our Sun could contain about 1.3 million Earths, via Canis Majoris, at 1,420 solar radii, could contain approximately 2.86 billion suns. Stephenson, 2.18, if the 2,150 solar radii estimate is accurate, could contain approximately 10 billion suns. 10 billion. That is more than the number of people who have ever lived on Earth. These numbers stretch the limits of human comprehension. We evolved to understand distances we can walk in a day, sizes we can hold in our hands, timescales of seasons and lifetimes. We did not evolve to grasp billions and trillions, but the universe does not care about the limits of our intuition. It operates at scales that dwarf everything we know. Now, let us turn to perhaps the most fascinating part of the entire story. What happens to these monster stars? What is their fate? Because everything that lives must die, and in the case of the most massive stars, death comes with a spectacle that outshines an entire galaxy. A star like Stephenson 2.18, or VY Canis Majoris, or RSGC 1F01, or any red supergiant in the upper mass range, is on a one-way journey toward catastrophe. Right now, these stars are fusing heavier and heavier elements in their cores, building up layers like the shells of an onion. At the very center is the most recently fused element, surrounded by shells of lighter elements being fused in succession. After the core finishes burning helium, it contracts and heats up further, and carbon fusion begins. The carbon burning phase lasts about 1,000 years, then neon burning, which lasts about a year, then oxygen burning, which lasts about 6 months, then silicon burning. Silicon burning lasts approximately 1 day. 1 day. After fusing silicon, the core is left with iron, and iron is the dead end of nuclear fusion. For every element lighter than iron, fusion releases energy. The nuclear binding energy per nucleon increases as you fuse lighter elements into heavier ones, up to iron. But iron sits at the peak of the binding energy curve. Fusing iron into heavier elements does not release energy. It absorbs energy. So when the core of a massive star becomes iron, fusion stops. And when fusion stops, there is nothing left to generate the outward pressure that has been holding the star up against gravity for millions of years. The iron core is incredibly dense and hot, but it is no longer generating energy. Gravity has been waiting for this moment. Gravity never stops. It has been pulling inward since the very first moment the star formed from a collapsing cloud of gas, and it has been held at bay by radiation pressure ever since. Now, with radiation pressure gone, gravity wins. What happens next is almost too fast and too violent to describe. The iron core, which has a mass of roughly 1.4 solar masses, the Chandrasekhar limit, can no longer support itself through electron degeneracy pressure. The electrons are forced into the protons, creating neutrons and neutrinos in a process called neutronization or electron capture. The core collapses. It does not collapse slowly, it collapses in milliseconds. The inner core plunges inward at speeds reaching 70,000 kilometers per second, roughly 1/4 the speed of light. In less than a second, the core, which was roughly the size of Earth, is compressed into a ball of neutrons about 20 kilometers in diameter. A neutron star. The density of this object is approximately 100 million tons per cubic centimeter. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. The outer core, which was falling inward along with the inner core, slams into the newly formed neutron star and bounces. This bounce sends a shockwave outward through the star. At the same time, the core releases an unimaginable flood of neutrinos, ghostly particles that normally pass through matter without interacting. But the density of the collapsing star is so extreme that even neutrinos interact with the infalling material, depositing energy that reinvigorates the stalled shockwave. The shockwave, now energized by neutrinos, blasts through the outer layers of the star, tearing them apart and hurling them into space at tens of thousands of kilometers per second. This is a supernova, a Type 2 supernova, specifically because the expelled outer layers contain hydrogen. For a few weeks, the supernova outshines its entire host galaxy, radiating as much energy as the Sun will produce in its entire 10 billion year lifetime. The light curve of a Type 2P supernova, the most common type from red supergiant progenitors, shows a characteristic plateau phase where the brightness remains roughly constant for several months. This plateau occurs because the huge amount of ejected hydrogen is recombining, releasing energy, and maintaining the luminosity even as the ejector expand and cool. For the most luminous and most massive red supergiants, the ones closest to the upper mass limit, the end may be somewhat different. These stars may have lost so much mass through their extreme stellar winds that by the time their cores collapse, they have shed most of their hydrogen envelope. They may have evolved back from the red supergiant phase to become yellow hypergiants, or luminous blue variables, or even Wolf-Rayet stars. In these cases, the supernova may be a Type 2b, with some hydrogen visible in the spectrum but not much, or a Type Ib or ice, with little to no hydrogen. The specific type depends on how much of the outer envelope remains. For a star like Stephenson 2.18, which appears to be experiencing extreme mass loss and may be on the verge of ejecting its outer layers, the final supernova could potentially be a spectacular stripped envelope explosion. Or, if the star maintains its massive hydrogen-rich envelope, it could produce a brilliant Type 2P supernova that would be visible to telescopes across vast distances. Given its distance of roughly 19,000 light-years, it would not be visible to the naked eye from Earth when it explodes, but it would be easily detectable by modern telescopes and would provide invaluable data about the deaths of the most extreme stars. There is another possibility for the very most massive stars. If the core that remains after the explosion exceeds approximately 3 solar masses, then even neutron degeneracy pressure is not sufficient to prevent further collapse. The core continues to shrink past the neutron star stage and becomes a black hole, an object so dense that its gravitational field prevents even light from escaping. For progenitor stars in the mass range of Stephenson 2.18 and similar hypergiants, the formation of a black hole is a likely outcome. Some theoretical models suggest that in extreme cases, the star might not produce a visible supernova at all. Instead, the core collapse might be so complete and so rapid that the star simply disappears, collapsing directly into a black hole without the dramatic explosion. This is called a failed supernova, and there is tentative observational evidence that it can happen. In 2009, astronomers monitoring a survey of nearby galaxies noticed that a red supergiant in the galaxy NGC 6946, a star roughly 25 times the mass of the Sun, simply vanished. It had been there in previous images, and then it was gone. There was a brief, faint brightening, much dimmer than a normal supernova, and then nothing. The leading interpretation is that this star underwent a failed supernova, collapsing directly into a black hole. If this can happen to a 25 solar mass red supergiant, it might also happen to the most extreme examples like Stephenson 2.18. Whatever the specific mechanism, the death of a massive star is not just an ending, it is a beginning. The material ejected in a supernova, the heavy elements forged in the star's core over millions of years, the elements created in the supernova explosion itself, all of this material is scattered into interstellar space, enriching the gas and dust from which the next generation of stars and planets will form. Let us take a moment to reflect on what this means. Every element in the periodic table heavier than hydrogen, and most of the helium was created inside stars. The carbon in your DNA was forged in the core of a star through the triple alpha process. The oxygen you are breathing right now was created during oxygen burning in the shells of a massive star. The iron in your blood was synthesized in the core of a star that went supernova. The calcium in your bones, the phosphorus in your cell membranes, the nitrogen in your proteins, all of it came from stars. But it gets even more remarkable. Elements heavier than iron, gold, platinum, silver, uranium, these are not created by normal stellar fusion. They require even more extreme conditions. Many of them are forged during the supernova explosion itself, in the intense neutron flux that occurs in the seconds following core collapse, through a process called the R process, or rapid neutron capture process. Others are created in neutron star mergers, the collision of two neutron stars. Either way, these elements require the deaths of massive stars. So when you look at a gold ring on someone's finger, you are looking at atoms that were created in the death throes of a massive star billions of years ago, scattered into a molecular cloud, incorporated into the gas and dust that formed our solar system, swept up into the rocky body that became Earth, mined from the ground and fashioned into jewelry. That gold ring is a supernova remnant on your finger. And the massive stars like Stephenson 2, 1-8 are the factories that make this possible. Without the short, violent lives and spectacular deaths of red supergiants and hypergiants, the universe would contain almost nothing but hydrogen and helium. There would be no rocky planets, no oceans, no atmospheres, no organic molecules, no life. We owe our existence to stars that lived fast and died young. This brings us to a broader question. Why does any of this matter? Why should we care about a star that is 19,000 light years away? A star we will never visit, a star that has no direct impact on our daily lives? The answer, I think, is that studying these stars teaches us about the fundamental nature of the universe we live in. Understanding red supergiants and hypergiants means understanding the engines that drive the chemical evolution of galaxies. The heavy elements created and distributed by these stars are the raw materials for planetary systems, for potentially habitable worlds, for life itself. Understanding how massive stars form, evolve, and die is essential to understanding why galaxies look the way they do, why they contain the mix of elements they contain, why some regions of a galaxy are actively forming stars while others are quiescent. Studying these extreme stars also pushes the boundaries of our understanding of physics itself. The Hayashi limit, the maximum size a convectively stable star can reach, is a prediction of stellar structure theory. When we observe a star like Stephenson 2, 1-8 that appears to exceed this limit, it forces us to ask whether our theory is incomplete, whether there are physical processes we have not accounted for, or whether the observations are misleading us. Either way, we learn something valuable. Science advances most when observations challenge theoretical predictions, because that is when we discover new physics or refine old physics. The technology developed to study these stars has broader applications as well. Stellar interferometry, the technique used to measure the angular diameters of red supergiants, has applications in other areas of astronomy and in engineering. The sophisticated radiative transfer models used to interpret the spectra and circumstellar environments of these stars advance our understanding of how radiation interacts with matter. Knowledge that is relevant far beyond stellar astrophysics. The Gaia spacecraft, which has revolutionized stellar distance measurements and single-handedly reshaped our understanding of stars like Scuti, has also provided the most detailed three-dimensional map of the Milky Way ever created, transforming our understanding of our own galaxy's structure. And there is something else, something harder to quantify but no less important. There is the simple, profound act of looking outward, of recognizing how small we are and how vast the universe is, not as a source of despair, but as a source of wonder. The fact that a creature standing on a small rocky planet, orbiting an average yellow dwarf star in one arm of a spiral galaxy, can discover, measure, and understand a star 2,000 times wider than its own sun. A star 19,000 light years away. That fact is one of the most extraordinary achievements of the human species. Think about the chain of knowledge that makes this possible. Ancient Babylonians and Greeks catalogued the positions of stars. Islamic scholars preserved and expanded astronomical knowledge during the medieval period. Tycho Brahe made the most precise pre-telescopic observations of stellar positions. Galileo pointed a telescope at the sky and changed everything. Newton formulated the laws of gravity and motion. Herschel discovered infrared radiation. Kirchhoff and Bunsen figured out spectroscopy, the technique that allows us to determine what stars are made of from their light. Hertz, Sprung, and Russell created their diagram. Eddington figured out that stars are powered by nuclear fusion. Hayashi determined the limits of convective stellar structure, and generation after generation of astronomers, building on each other's work, using ever more sophisticated instruments, from the 2-micron all-sky survey that revealed the Stephenson 2 cluster, to the very large telescope that measured Scuti's angular diameter, to the Gaia spacecraft that refined stellar distances across the galaxy too. The James Webb Space Telescope that is revealing the universe in unprecedented infrared detail. Every step along this chain was necessary to bring us to the point where we can say with confidence that a star roughly 2,000 times the radius of our Sun actually exists.